Welcome to VTU Bros Hub. We're covering the most repeated and expected questions from Graph Theory Module 1, directly based on VTU's CBCS 22 scheme. These are the questions that keep repeating in model, makeup, and regular exams. If you prepare these, you can easily score 20 out of 20 in Module 1. Let's go! Let's begin with the first question. Define isomorphic graph and check whether the given graphs are isomorphic or not. This question is commonly asked for 7 marks, and it's easy to score if you understand the meaning well. Now imagine you have 2 different diagrams, but both are actually showing the same network, just drawn differently. That's what isomorphism means in graph theory. So what's the definition? 2 graphs are called isomorphic if they have the same number of vertices, the same number of edges, and a way to match vertices from one graph to the other, so that connections between them stay the same. It's like this. Imagine you and your friend have the same model of mobile phone, but yours is in black color and theirs is in red. The color is different, but the internal features are the same. Similarly, 2 graphs can look different, but if their connections are the same, they are isomorphic. Now, in the exam, they may give you diagrams labeled Graph A, Graph B, Graph C, and so on. You have to follow 3 steps. Step 1. Check if the number of vertices and edges are equal. Step 2. Check if the degrees of each vertex match. Step 3. Try to find a one-to-one mapping of the vertices that preserves the connections. If all 3 conditions match, then the graphs are isomorphic. For example, if vertex A is connected to B in graph 1, then vertex X must be connected to Y in graph 2, based on your mapping. In your answer sheet, always mention the mapping clearly, like A to X, B to Y, C to Z, and say, yes, the graphs are isomorphic. If they do not match in degree or structure, just say, no. The graphs are not isomorphic because the degrees do not match. This is the answer. You can understand it easily. Keep the structure same like this in your exam to score full marks. Let's now move to the second question. This is a standard and important theory question. Prove that the number of vertices with odd degree in a graph is always even. It carries 7 marks. Let's understand it in a simple way. In any undirected graph, every edge connects 2 vertices. So, if you count the degree of every vertex and then add them all, you're basically counting each edge twice. That's why the sum of degrees of all vertices is always even. Hence, the number of vertices with odd degree in a graph is always even. This is the answer, and you can understand it easily. Keep the structure same like this in your exam to get full 7 marks. Let's continue with the third question. Show that a simple graph with n vertices and k components can have at most open bracket and minus k close bracket times open bracket, n minus k plus 1 close bracket divided by 2 edges. Let's simplify this. A component is a separate connected part of a graph. If a graph has k components, we get maximum edges by placing n minus k plus 1 vertices into one component, and keeping the remaining k minus 1 as isolated vertices. Now, a complete graph with n minus k plus 1 vertices has at most n minus k times n minus k plus 1 divided by 2 edges. The isolated vertices don't add any edges. So the maximum number of edges in such a graph is open bracket minus k close bracket times open bracket, n minus k plus 1 close bracket divided by 2. This is the answer. You can understand it easily. Keep the structure same like this to get full 7 marks. Let's now move to the fourth question. Show that the maximum number of edges in a simple graph with n vertices is n times open bracket n minus 1 close bracket divided by 2. In a simple graph, there are no loops or multiple edges. So the maximum number of edges is just the number of unique pairs of vertices. That's a combination, and choose 2, which equals and multiplied by open bracket, n minus 1 close bracket divided by 2. Example, 5 vertices give 5 times 4 divided by 2 equals 10 edges. This is the answer. You can understand it easily. Keep the structure same like this to score 7 out of 7. Now we are at the fifth question, a fixed 8-mark theory question. Define a graph and explain the types of graphs. Let's start with the definition. A graph is a pair of sets, G equals open bracket V, comma, E close bracket, where V is the set of vertices and E is the set of edges connecting those vertices. Think of vertices as points and edges as the lines between them. For example, cities as vertices, roads as edges, or users on Instagram as vertices and follows as edges. Now let's briefly explain the important types of graphs, all shown clearly in your PDF notes. Null graph. No edges, only isolated vertices. Trivial graph, only one vertex, no edges. Undirected graph, edges with no direction. Directed graph, arrows show edge direction. Finite graph, has countable vertices and edges. Infinite graph, has endless vertices and edges. Multigraph, allows multiple edges, no loops. Pseudograph, allows loops and multiple edges. Simple graph, no loops, no multiple edges. Draw neat diagrams just like in your notes to score full marks. This is the answer. You can understand it easily. Keep the structure same like this in the exam to get full 8 marks. Let's now go to the 6th question. Explain the applications of graphs. This is a common 7-mark theory question, and you should write 5 standard uses of graphs to score full marks. Number 1, application in computer science. Graphs are used in many computer algorithms like Dijkstra's, Prim's, and Kruskal's algorithm. They are used to define the flow of computation, represent networks and data structures. In networking, web pages are vertices and hyperlinks are edges. In social media, people are vertices and connections are edges. Graphs help solve problems like finding shortest paths, detecting cycles, and memory optimization. Number 2, in field science. Graphs are used in fields like biology, chemistry, and physics. In chemistry, molecules are graphs with atoms as vertices and bonds as edges. In biology, graphs model genetic networks, protein interactions, and drug target mapping. In physics, they are used to show complex systems like energy or signal flow. Number 3, Konigsberg Bridge problem. This is the origin of graph theory. The city of Konigsberg had 7 bridges, and people tried to walk through each one only once. Euler represented the bridges and land as a graph and proved it's not possible to do that without repeating. This introduced the concept of Eulerian paths. Use the diagram from your notes. It's great for scoring bonus marks. Number 4, utilities problem. This is a puzzle with 3 houses and 3 utilities: water, gas, and electricity. The challenge is to connect every house to all utilities without crossing lines. Graphs help show that this is not possible in a plane, which introduces the concept of non-planar graphs and graph coloring. Number 5, electrical networks. In electrical circuits, graphs are used to analyze current flow, calculate voltages, and apply Kirchhoff's laws. Vertices represent resistors or batteries, and edges are wires. This is very useful in circuit design and electrical engineering. In exams, write all 5 clearly with one-line examples. Draw diagrams for bridge and utilities problem. It shows you know the concept well. This is the answer. You can understand it easily. Keep the structure same like this and you'll get full 7 marks. Let's go to the 7th and final question. You have to explain 12 important terms from graph theory. These are small questions, 2 to 3 marks each, and come in almost every VTU exam. Let's go through them one by one. 1. Walk. A walk is a sequence of vertices and edges where both may repeat. Refer to the diagram in this PDF to all. 2. Path. A path is a walk with no repeated vertices. Examples shown in the PDF notes. 3. Circuit. A circuit is a closed path starting and ending at the same vertex. 4. Bipartite graph. Vertices are split into 2 sets. Edges go only between sets. 5. Complete bipartite graph. Each vertex in one set connects to every vertex in the other set. 6. Subgraph. A smaller part of the graph with some vertices and edges. 7. Regular graph. All vertices have the same degree, like all are 3. 8. Complete graph. Every vertex connects to every other. If there are n vertices, total edges, Subgraph, n times n minus 1 divided by 2. Diagram proves it. 9. Open walk. A walk where start and end vertices are different. 10. Cycli. A closed path with all distinct vertices except the first and last. Visual shown in your PDF. 11. Trail. A walk where no edge repeats, though vertices can. See the trail example in the notes. 12. Pendant vertex. A vertex connected by only one edge. Degree 1. In exams, write a short definition and draw a small diagram if space is given. This is the answer. You can understand it easily. Keep the structure same like this, and you will score full marks. This completes the 7th and final question.